Hello everybody, welcome to the first Sciencetech webinar series, Versatile Solar Simulators for Unlimited Research Opportunities. My name is Xiaoxi and I'm joined here today by my colleague Hirini, and we're both application scientists here at Sciencetech. I hope this webinar will be useful for you, so let's get started.
Okay, just to give a quick recap before we start our webinar, this is going to be the first of a series of webinars we would like to host as educational content for our customers. This is extended to you as a token of appreciation for showing interest in our company. We want to start from the basics of solar simulators, starting from why we use solar simulators and how to use the right solar simulator for your research and industrial needs. Research opportunities are unlimited if you use the correct solar simulator. So we want to guide you through this process from A to Z. We then discuss different classifications of solar simulators and follow that with a brief description of our ultra-high efficiency solar simulator. We do have a chat window where you can type your questions, but do wait until the end of the webinar to ask your questions. So let's dive into the webinar.
Thank you, Hirini. So first of all, we would like to give a quick introduction of who we are. Sciencetech manufactures solar simulators and optical spectroscopy instrumentation for over 33 years, and we're located in London, Ontario, Canada. Over the years, we have collaborated with many reputable research institutes such as national space agencies and universities. Our instrumentation ranges from research-grade light sources to integrated solar simulators and spectroscopic systems. Our company is also well known for providing custom solutions and designing equipment to fit into your unique research projects.
Right. Thank you, Xiaoxi, for that introduction. So, why do we use a solar simulator and not just any other light source that gives off white light? Well, solar simulators are used to provide illumination that closely resembles natural sunlight so that indoor testing can be conducted to check the performance of different devices and conduct different solar research projects. So, characteristics of the simulated solar light has been regulated to comply with standards for different applications. These applications can be to test photovoltaic devices such as solar panels, photochemical batteries, or even to test cosmetic products. It could also be to test thermal power generators and also test consumer electronic goods such as cell phones, cameras, and photochromic lenses. Or it could be used to test industrial or building materials such as plastics, paint, and textiles. Now, solar simulators can also be used for research studies in biological and medical sciences such as cancer research, photosynthesis studies, and biosensor analysis.
So, why is solar energy so important to us? Earth's primary source of energy is radiant energy from the sun. The amount and intensity of solar radiation that a location receives depends on a variety of factors. These factors include latitude, altitude, season, time of the day, and cloud cover, and so forth. Not all radiance emitted from the sun reaches Earth's surface. A lot of it is absorbed, reflected, or scattered in the atmosphere. On the Earth, solar energy can be absorbed directly from the sun. Now, this is called direct radiation. Another type of radiation is from light that has been scattered as it enters the atmosphere, which is called indirect radiation or global radiation. With a solar simulator, radiation observed at different conditions of the Earth can be simulated with the use of filters and optical configurations. Solar simulators can also imitate solar radiation observed in space. Now, we will discuss how to imitate these different forms of solar radiations in a moment.
Right. Now, if you open a solar simulator, you'll find that essentially it's a lamp source with carefully assembled optical and electrical components. There are a few main components that one must take into consideration. We will have a lamp source in varying wattages. These wattages will depend on the illumination area, how uniform you want the light source to be, and also how collimated you want the light rays to be. The lamp source will be inside a lamp housing, which is essentially a light-tight enclosure will have optical components such as lenses, back reflectors, and an igniter. The solar simulator will also contain a power supply for the lamp. There's also an air mass filter used to filter the light beam to match the solar spectrum. These air mass filters can vary depending on the type of spectral conditions you want to imitate. Optionally, you can also include neutral density filters to change the intensity of the light. We can also add long and short pass filters to isolate certain parts of the wavelength spectrum.
Right, so to sum up, what makes a solar simulator different from a light source is its ability to mimic solar light. There are a few main characteristics that we must consider. As we mentioned earlier, these characteristics are standardized for different testing applications. The solar simulator should be able to produce a close match to the sun's spectrum. It should produce a spatially uniform area of illumination just as the sun does. It should also produce a steady output over a standardized period of time.
Right.
Optionally, the simulator should be able to give the same power density as at the illumination area as the sun. Now, some applications require the light beam to be highly collimated, so our solar simulators can produce such illumination as well.
Right. So let's look at these characteristics in detail. The first characteristic we are going to be discussing is the solar spectrum. The figure on the top left. Okay, we're back. The figure on the top left shows the wave bands of the spectral distribution for different reference conditions. There's the terrestrial direct spectrum, which is AM 1.5D, shown in the figure in blue. There's also the terrestrial global spectrum, which is AM 1.5G, shown in green. And there's the extraterrestrial spectrum, or what we call the space spectrum, in AM0, which is shown in red. We will explain these different spectrums in a minute. The figure in the bottom right corner is a comparison of the AM 1.5G spectrum to one of our own solar simulators, SF300A. So as you can see, it's a pretty good match. Now, standards have been developed to regulate how well the spectrum of the solar simulator matches that to the sun. Mainly for photovoltaic testing, 3 classifications are followed. There's classes A, class B, and class C, with A being the closest spectral match to the sun, and class C being the minimum requirement to be called a solar simulator.
Okay, right. So in order to achieve the spectral match classifications, air mass filters are used to imitate solar spectra for different conditions. In this figure, you can see that solar radiations are received on different areas on Earth. If outer space simulation is required for research, then an AM0 filter will be used to simulate this type of spectrum. Now, besides AM0, which is common for space research, the most commonly used air mass filters, AM 1.5 global, which gives the sun's spectrum under most terrestrial conditions. We also have other air mass filters to simulate special conditions, such as the solar spectrum near the equator or the polar regions. Now, pictures on the bottom right corner shows what an air mass filter actually looks like.
Right. Okay, so another important characteristic of the sun is its spatial uniformity. Now, as a light source, sun produces an extremely uniform illumination. Therefore, uniformity of the output beam of a solar simulator should ideally be as uniform as the sun. Now, it's impossible to illuminate a target area as uniform as the sun. We can use special optical components and homogenization lenses to achieve this characteristic in a solar simulator. This specification is measured by essentially dividing the target area into a number of equally sized areas and mapping the irradiance in each individual square. In other words, we're trying to find the number of photons hitting each square area, which should ideally be the same. This ensures that the target area covered by the simulator is accurately and consistently illuminated. Similar to spectral match that we discussed earlier, spatial non-uniformity also has class A, B, and C. Here, according to ASTM standards, class A gives 2% non-uniformity, class B gives 5% non-uniformity, and C gives around 10% non-uniformity. So on the left, in your slide, you can see an irradiance distribution map to assess the uniformity of one of our solar simulators, which is SF300A.
Next, we come to another important characteristic, which is the temporal stability. The sun, as a consistent source of power, has an irradiation that is very stable. Now, temporal stability tests how stable the output power is of a solar simulator. If there are drastic fluctuations in the irradiation of the solar simulator for a given amount of time, it is not very stable. So to standardize this property of the solar simulator, standards such as ASTM for photovoltaics regulate the test duration for temporal instability. In this way, the consistency of the output power is classified by class A, B, and C as well.
Right. So besides temporal stability, solar irradiance is also important for most research projects. Now, solar irradiance is the intensity with which radiation enters Earth's atmosphere. Solar irradiance is the amount of radiant flux on an area, and it's measured in watts per square meter. In AM 1.5G spectral conditions, natural sunlight gives around 1,000 watts per square meter, which is defined as one sun in this case. If your research requires more than one sun intensity, or you want to use different conditions, our solar simulators can provide that for you.
But the sun is so far away from the Earth that the solar rays that incident on Earth are nearly parallel to each other. Their convergence angle is 0.53 degrees. So for all intents and purposes, the sun rays can be considered as highly parallel, or in other words, collimated. This makes collimation angle an extremely important role for concentrated voltaic testing and space-related research that requires conditions very similar to the sun. Now, Sciencetech has many proprietary designs for highly collimated solar simulators. This is an example. In the bottom picture, this is an example of a highly collimated solar simulator that we built for space agency. This beam output of the system provides 0.7 divergence angle, which is very close to the sun's conditions. Here, we have used a complex optical design to produce these highly collimated beams. If you would like to further discuss these types of highly collimated solar simulators, do feel free to contact us for more information.
Now, our solar simulators are tested to comply with ASTM standards, but there are many standard organizations such as IEC and JIS that our solar simulators can comply with. These standards regulate mainly spectral match, spatial non-uniformity, and temporal instability, which we discussed earlier. But each of these standard organizations have standardized different ways of testing the said specifications. Now, our system can also comply with other more distinct standards such as COLIPA standard for cosmetics and skincare industry. Our application scientists can further discuss with you regarding these specifications and standards. Now, with the general classifications and applications of solar simulators being introduced and discussed, the educational section of this webinar has come to an end. But please feel free to stay with us for another couple of minutes to hear about Sciencetech's ultra-high efficiency solar simulator.
Right. Thank you for still staying with us. So our ultra-high efficiency solar simulators have been designed to produce extremely efficient electrical to optical conversion. Now, these simulators are feature-rich, convenient integrated systems and are suitable for a variety of research. The solar simulators can also produce one sun or more solar radiance on a variety of solar spectral classifications. Now, strict quality control procedures are performed to ensure that the solar simulator meet the required specifications. The simulator can be controlled from just a single touch screen interface. And the solar simulator is highly integrated, and it even provides a fully leveled sample stage for you to place your test samples. Now, we have a bunch of different UHE models that can provide different target areas, and horizontal or vertical beam output can be configured as well. Also, we would like to provide a 15% discount on our UHE series solar simulators today to all our participants of this webinar.
Right. Okay. So now that we have come to the end of our webinar, if we have some time to discuss any questions you might have about the contents that we discussed today. So you can type to us through the chat window. And we are also joined by Dr. Andrew Brzezinski, our head application scientist. So if you have any questions, now is the time to ask them and we'll respond. Okay?
Thank you very much.
Thank you.